There are a few problems on the group quiz that people still had some issues with, so I wanted to kind of go over those and cover that material. So one of them was the working on the flipping these chair conformations. And so when we're doing this, remember we need to make our little lightning bolt. What I recommend is moving these clockwise and rotating them to one position over, and then changing them from equatorial to axial and vice versa. So when we're doing that for this compound here, we're going to want to look at this bromide or bromine is going to go in the axial position here, and then it's going to go equatorial in the next position. So remember when we're drawing these in axial versus equatorial, all of the points go point up or point down straight. Those are the axial positions, and then all the other ones are equatorial, and those point on the bottom of the ring or the top of the ring, depending on it's the opposite side of the ring. So if this is pointed up here, straight up and down, this one's going to point down slightly because it's on the other side of this ring. So that's when we kind of go like this. If we're going to make that a hexane, one part of that's going to come in this orientation with a wedge, and the other is kind of on the other side. So this one's kind of down below, and this one's on top. So that's why here, if I go down, this one's going to be slightly up. Here, if I go down, this one's going to be slightly up. So this one's up, this one's slightly down, pointed outside. This one's up, this one's going to be pointed slightly down, and then this one's down, so this one's going to be pointed up. So that's how you should be drawing those, and that's important because it tells you if these are cis or trans. So we'll come back to that in a second. This one a lot of people had wrong as well, and with this sp3 hybridized carbons, these are able to freely rotate. These are actually conformational isomers. So just the conformation has changed. The constitutional means that there is a change in where the different elements are attached to each other. That's different. And this is a conformational isomer, not a constitutional isomer. When we come over here, this is again drawing these out, these ring structures out, and kind of looking at how they fit on each other. This one is more difficult to see, but again, you notice that this is pointed up and this one's pointed down. That's telling us that this OH group is on the top side of the ring. This OH group is on the bottom side of the ring. So these are on the opposite side, so they're actually trans. So when I draw this out in this format, sorry, this is pretty bad, they're going to be, one is going to be on one side of the ring, and one is going to be on the other side of the ring. And that's how that would look. If we're going to redraw that structure in this chair conformation, if we're going to rotate these to kind of see what it would look like when it flips, this one is going to flip from the equatorial to the axial position, and then the other one is going to flip from the equatorial to the axial position here, and you can see how that would point up the OH and down the OH. So you can really see that that one is going up and one is down. Same here, so that's going to be that trans conformation. So these kind of being able to kind of do this, that's important to be able to see how these things are oriented. And especially if you are not really great at the equatorial, if it's pointed up or down, swapping them here should make it a little more easier to see if they're on the same side or the opposite side. And finally, this last one with oxidation reduction, this was tricky for some people, and again, looking at the oxidation numbers and how they change or the same, really want to look at differences between the two. So if we're kind of looking at these two spots here, these carbons, and the carbon over here, if we look at the oxidation number, we basically have, if we're looking at one of the carbons from each of those bonds, so we're going to say that it has 2 electrons in that format, and then we come over here. And this isn't the same as oxidation number, right? So if we start with 4 electrons, then we go to 2 electrons, that means that it was a plus 2 oxidation number. But right now we're just going to look at the change from one spot to another. So here it just kind of has 2 electrons. Here on the other hand, right, it gets 1 from this bond, 1 from this bond, 0 from the top bond, but there's also an inferred hydrogen that's not being shown there. To have 4 bonds, we'd have to have a hydrogen there. So it gets 2 from the hydrogen and then 1 from each of the other sides, so it actually has 4 electrons. So we go from 2 electrons to 4, but then let's look over here. So this carbon had a hydrogen here, so that carbon had 2 from this bond, 2 from that bond, so that's 4, 5, and 6 electrons, and then we go over here, and now it loses the 2 from the nitrogen, it still has 2 from the hydrogen, and then it has 1 from each one, so 1, 2, 3, 4 electrons. So we go from 6 and 2, this total is 8 electrons, and then we get 4 to 4, so it's still 8 electrons. So there's no difference. We go from 8 to an 8, so there's no gain of electrons is reduction, loss of electrons is oxidation. Well, it's the same, so it's neither. Here we can see that we lose oxygen to carbon, so that one's kind of quick to see that. So we are doing the opposite of oxidation, so that's a reduction. Same here, and we go from 2 carbon oxygen bonds to 1 carbon oxygen bond, so also a reduction. And you can do the same looking at the oxidation numbers. That also works. So we're going to do the oxidation numbers again here. So we're looking at these 2 carbons. This is where the changes happen. So here we have hydrogen, hydrogen at both sides, hydrogen, hydrogen. And here we just have 1 hydrogen because we're go from sp3 to sp2 hybridized. This carbon here, we get to count both of these. That's 2, 4, 5, and 6 from the bond, 6 electrons. And then we go over here, and this carbon now only has 2 from the hydrogen, and then 1 from each of those double bonds. So it's 2, 3, 4, and then 1 from the other side, 5. So we have 5 electrons. So this is going to be the same. We also have 6 electrons here. It'll be the same kind of math, and then 5 electrons here. So we go from 12 total electrons to 10. So we go from 12 electrons to 10. We have a loss of electrons, so that's oxidation. So these, a few of you had some problems with this section and some of the other ones that I just mentioned. So I just wanted to walk through those, make sure that we're all on the same page heading into the midterm exam.